Hey, what's up, y'all? It's Mr. Byros. I'm just making a quick video to go over some of the problems from the Kinematics multiple choice questions that we did a while back, just to review and focus in on some of the ones that gave people more trouble, so that hopefully we can look back and see what things are more difficult or more tricky for people as a whole and get some answers on what's going on with those. So the four that people missed most frequently were the first, second, third, and 12th questions. Now, first and second, there was two options, or there was supposed to be two options. So the correct answers were A and D. Now, a lot of people chose A, but a lot of people also chose C. So let's look at the question and see what was going on here. So the first question asked, objects moving with constant speed traveling once around a circular path. Which of the two following statements are true concerning the motion? Now, the two true statements are the displacement is 0 and the velocity is changing. Now, displacement measures your initial and final positions, and if you end up at the same exact point that you started at, your displacement is 0. Most people got that. Now, the acceleration is not 0, because if an object is moving in a circle, in a circular path, you have centripetal acceleration for circular motion. And D is correct, because the velocity is changing. The tangential velocity of the object as it goes around in a circle does change. So D and A are correct. C is incorrect because there is some centripetal acceleration. Even if the speed is constant, the velocity changes direction and you have acceleration. So let's look at number 2. For number 2, looks like A and B, it was pretty even, but A and B got a lot of answers on that one. So here's number 2, and it says in section 5 of the velocity time graph, the object is, and the correct answer for 5 is slowing down, moving in the negative direction. Now, if we just look in section 5, we can see that the velocity is negative. At every point in section 5, it's below the x-axis. So the part where the object is moving in the negative direction, we could get that. It has a negative velocity the whole time. But what's happening to that velocity? So initially right here, we've got a velocity of a larger negative number. So this could be like -3 meters per second. And then it goes to 0 here. So if the object goes from -3 meters per second to 0, the object is actually slowing down. The acceleration is, this would be like if you were going backwards in your car, which you could say is the negative direction, and you were going -3 miles per hour or meters per second, then you ended up slowing down and pushing on the brake until you stopped. Even though you were going in the negative direction, you're still slowing down, putting on the brake, decelerating. So D is correct because it is moving in the negative direction, but it's not speeding up just because the slope is upwards. Speeding up, slowing down asks the question, is the magnitude of the velocity decreasing or increasing? And in section 5, the magnitude of the velocity is decreasing. It is going from a larger negative number, a larger absolute value of the number, to a smaller absolute value of the number. All right, we had number 3. Another one that had two options. C was one that people kind of were picking on this one for an incorrect answer. So let's look at number 3 and see what's going on there. Number 3 says, which of the following statements are true about uniformly accelerated motion? Select two answers. Now we saw from that B and D, I believe, just double check. Yeah, B and D were the answers. Uniformly accelerated motion, if an object's acceleration is 0, its speed is going to remain constant. That's true. If the acceleration is 0, the magnitude and direction of the velocity are not changing at all, so the speed must remain constant, because the speed is just the magnitude of the velocity. D is correct because the object's direction of motion is changing. So if you had, again, something going in a circle, circular motion, the direction is changing. So even if the magnitude of the velocity stays the same, it's accelerating. That would be like our centripetal acceleration, for example. And C, the one that was tricky here, said an object's speed remains constant, its acceleration must be 0. So that is not true because a speed could remain constant, again, as you're going in a circle for circular motion. The acceleration, you could have centripetal acceleration as an object's going in a circle, even if it has constant speed. So you could go around at the same rate. You're not speeding up or slowing down how quickly you're spinning it in a circle, but it is accelerating because the direction is changing. So speed remains constant. You also have to have the direction remain constant if acceleration is going to be 0. Last but not least, number 12, all the way down here. Car brakes. Now this one pretty clearly A was the problem that was tripping people up. So C was correct. A was the tricky one. So a car traveling at an initial speed of v0 applies its brakes, skidding to a stop over a distance of x meters. Assuming the deceleration due to the brakes is constant, what would the skidding distance of the same car be if it were traveling with twice the initial speed? Now 2x is the tricky one because we might think, oh, if it's twice the initial speed, it would take twice as far to stop. But this is actually a really important and key note for driving, because if you're driving, you might think, oh, if I'm going twice as fast, it'll just take me twice as far to stop. However, let's look at the solution for this one, which I have here. So number 12 says, the variables involved in this question are the initial velocity, the acceleration, the final velocity is 0 in both cases if you completely stop. And the displacement is your skidding distance or your stopping distance if you were driving in a car. And the missing variable is time, so we can use the big 5, number 5. This is they call it the big 5, number 5 in this book. This is our third equation from the equation sheet. Final velocity squared equals initial velocity squared plus 2 acceleration times the displacement. So displacement is going to be, we know that the final velocity is 0, so this v squared is going to be 0. If we double this, how the displacement changes is we're doubling this and then we're also squaring it. So if you double it and then square it, it goes up not by a factor of 2, but by a factor of 4. When the initial velocity is doubled, the final position, or the displacement, the stopping distance for this car, quadruples. So this is, again, one that whenever you're looking at doubling and seeing what happens if you double something or you triple something, it's always important to know what equation determines that relationship. So the relationship between initial velocity and the stopping distance for a car is in fact our v squared equals v naught squared. I don't think they have the initial velocity is a little weird. Plus 2 acceleration times the displacement. And because the velocity is squared, the stopping distance quadruples when you double the initial velocity. So important to know, if you're driving and you're driving twice as fast, it will take you 4 times as long to stop as if you were going half that fast. All right, so those are some of the kinematics questions. If you have any other specific questions, you can always email me or ask me to go over any of the things from that unit at any point before the test, the AP test if you're taking that. And yeah, that is it. Thanks, y'all.